I think we can start already with the introductions and the webinar. Okay, so my name is Eduard Piqueras. I work in the European Programs Unit in Eurecat. I am a former project coordinator of the Marvel project, and I would like to welcome you all to this first webinar of Marvel. Okay, Marvel is an European collaborative research and innovation project, okay, where different partners, European partners, are working together to develop an innovative and competitive lightweight battery with the objective to accelerate the mass market take-up of electric hybrid vehicles. Okay, the project was funded by the Horizon 2020 Research and Innovation Framework Program of the European Commission. And you will see in our agenda, for the structure of how we structured the agenda, part of the research and development that is being carried out in the project concerns the lightweight materials for electric vehicles. So that it comes from the use of novel lightweight materials, but also topics regarding the design, eco-design, and welding and joining. Okay, so you will see we will start with a presentation from my colleague Alberto Gomez, that's the technical coordinator of Marvel project, to introduce the project and our main goals. Then we will talk about lightweight material solutions for weight optimized battery housings, and this part Manuel da Silva from Metallic and Ceramic Unit in Eurecat and Christian Hahnemann from Fraunhofer IBU will talk us the advances that we made in Marvel project concerning this topic. Then we will our colleague from Eurecat, Francisco Fernandez, will talk about eco design and simulation, and finally Magnus Eriksson from SINTEF Research Center in Norway will give us some new advances in welding and joining techniques, okay, for reinforcing materials. So I would suggest to start with the first presentation that, as I mentioned, my colleague Alberto Gomez and me, we are coordinating the Marvel project. Alberto from a technical and scientific point of view. He's a technical coordinator. He has a PhD in nanoscience and nanotechnology from the University of Barcelona. And he has large experience in the automotive industry until joining Eurecat in 2019 as a head of electric mobility and energy storage. Okay, in the last decade he has led and worked on research and development projects for energy storage in batteries of the future, and also hydrogen, electric mobility in European and South American regions, energy efficiency optimization, or chemical simulation, among others. So welcome also Alberto to this meeting. I give you the floor to introduce the project and the main challenges we are facing together in this project.
So morning all, and thank you, Eduard, for this kind introduction, and also to the audience for the interest in this webinar. So this first speech of the session, I would like to briefly talk about the current and future challenges in the electromobility sector and why Marvel, let's say, it's important to tackle them. So the last selective vehicle renaissance, let's say, started with the Kyoto Protocol that lasted until 2012, where the plans, let's say, were defined to reduce the transport emissions. And the Doha Amendment tried to continue this trend, but negotiations failed and was not accepted until 2020. But nevertheless, Paris Agreement, which was planned to be updated periodically from 2016 on, likely continue to the emission reduction goals. And then in the COP26 held in Glasgow, November 2021, stated that 2040 was the deadline for stop producing and commercializing non-zero emission vehicles. And following that, probably you already know, there is some noise. Probably you already know that the European Parliament approved last February that the new carbon dioxide emission reduction targets for new passenger cars and light commercial vehicles was as a part of Fit for 55 package was executed. No, so the name Fit for 55 stands for setting in 2030 the emission targets at 55% reduction for cars and 50% for vans compared to those in 2020 emissions. And in addition to those targets, the new legislation sets that the path towards zero carbon dioxide emissions for new passenger cars and light commercial vehicles in 2035 is zero. So 0 grams per kilometer from 2035 on. And as you can see here in this figure, for example, Spain is clearly not keeping the pace so far. So with this, the battery sector continuously to exponentially grow in market for road mobility applications due to this strong electrification of transport that the EU Parliament is demanding for 2035. And in these figures shown here, you can see that which actually they're the same in terms of terawatt hours in numbers, let's say, but expressed as by mode and by region on the left and on the right. And the peak, the two probable scenarios in 2030. So stated policies and current plans, let's say, the steps, and the announced pledge or plans scenario, the APS ones, no. But also those numbers are not updated with the EV numbers needed in 2035, let's say, but at least 0.5 terawatt hours of battery demand will be necessary for Europe's electric vehicles in 2030, which is actually the 85% of all batteries that will be manufactured worldwide will be included in electric vehicles in this year. No, so in addition, batteries are increasing in size to withstand larger autonomy demand, and on the other hand, state-of-the-art batteries design nowadays is not intended for subsequent disassembly, direct application for second life, or recycling. No? And instead of thinking about circular solutions in mobility, let's say society is rushing to replace all combustion engines for electric ones. But however, not only is necessary to contribute to the research, technology, and innovation muscle to the current automotive industry and battery sector to achieve these goals, but also we have to really focus on the sustainable side of it all, because otherwise we will have a serious waste management problem sooner rather than later in our countries in Europe. So in addition to, in addition to that, the current situation in Europe further demonstrates the enormous dependence of the geopolitics on the supply, material prices, and transport of components, right? So this picture shown here is only an example of a possible path that materials, cathode cells, and batteries might follow before being included in an electric vehicle. No? And also, for example, we might substitute the path to the US for cell production, leave it in Asia, but then adding another path to the US for battery production anyway. So it's but then the battery might travel then somewhere to be integrated in a vehicle. So at the end of the day, every one of these intermediate paths is not emission-free at all. That's what I wanted to say, no? And also this picture depicts how Europe is losing track within the worldwide battery and EV value chain, no matter how much experience we have had in the past in the automotive industry, no? So therefore, Europe must provide sustainable, innovative solutions to deal with these challenges that while improving performances. And this is why Marvel is one of the European projects that represents one of these innovative solutions. No? Marvel's main goals and results are geared towards developing long-life batteries, complemented by improved performance and safety, short and more efficient charging times, and will create tools as well, platforms and models that will help reduce the development time and cost of the batteries. And each of these Marvel objectives fit within the 4 circular economy categories that the European Commission defines. So the design and production, the use, value recovery, and the support. No? And The fact that we have an OEM as important as Stellantis, so Fiat, CRF here, in the consortium also brings Marvell closer to the reality of the requirements that needs of this sector. No? So, for example, eco-design is a key element through the entire project. And in this sense, Marvell will take a key step forward, new materials, so recycled and recyclable, and design, and which is the topic of this webinar, and that will be expanded by my project colleagues in EURECAD, Fraunhofer and SINTEF later today. But with the aim of reducing weight without losing sight of the circular economy objectives, the research and development of housing with high content of recycled aluminum is addressed here. So to do this, EURECAD will evaluate what affects the impurities present in the aluminum scrap and what of these effects have on the mechanical and extrusion properties. Then ASAS in Turkey will carry out the metallurgical simulation and procedures of aluminum alloys to be extruded, and then EURECAD will study the extrusion of these alloys to generate the housing following an optimization of the profiles and design that will lead to this new design of the housing. Then SINTEF will lead the joining of the recycled aluminum profiles to manufacture the housing, and then actually Magnus will talk about this here today, and also Marvell approaches of the design for this assembly will be performed with a modular design as well as contacts, thanks to the solution of Fagrati that incorporates to the project and allows both the automatization of this assembly and the repairability of the battery while extending its application to second life. No? So modular also means that the Marvell project batteries are easy to scale and are valid to both light and heavy vehicles, so for all OEMs. But Marvell also develops advanced VMS led by REC, and with the objective of improving the efficiency of the battery and extending the useful battery life. This new VMS will include innovative features that will facilitate the use of technology developed for many other applications. So these developments, which will include security layers, will provide flexibility and modularity with the idea that the system is independent of the type of cells and the vehicle, as well as also adaptable through updates to other applications in second life. And to this end, artificial intelligence from our colleagues in Greece, ICCS, will be incorporated with the aim of providing correct estimation of the cell performances, as well as offering remote fault detection, diagnosis, and continuous improvement. No? OTC, our colleagues OTC, their smart cell manager that they will develop here will oversee and monitor signals such as cell voltage and temperature, and sending them wirelessly to the VMS, allowing remote configuration and assistance to be included. On the other hand, issues of cybersecurity and human-machine interfaces will be also considered by our colleagues from THI. And in France, PowerTech will be in charge of incorporating into the VMS both models developed by SCCS and the secure wireless communications. No? But other necessary solutions to extend battery life and decrease the recharging time and the environmental impact are related to the thermal management system, and also on the ultra-fast charging technologies that will be led respectively by the ADA and FICOSA. No? And to carry out this thermal management challenge, EURECAD was leading the study of the behavior of cells from the thermoelectrical point of view. Then Fraunhofer was defining the necessary heat dissipation materials, and both IDIADA and EVL Germany were designing and manufacturing the new cooling system or thermal management system in an innovative way with a new also control strategy. Then for the ultra-fast charging point of view, FICOSA was leading the development of strategies and components that are necessary to make this ultra-fast charging possible. AVL Italy then will pull everything out in the project, all that I previously mentioned to assemble the batteries of the project. And after the validation from the functional safety point of view, Terza Cupil will develop a rapid procedure for automatic disassembly of the battery for second life and recycle purposes. And after this, AVL Italy will then reassemble the battery to confirm the versatility of the process. And lastly, let's say the flexible, versatile, and modular test bench of the project for sake of the validation process will be built and will simulate the battery integration conditions in an electric vehicle without the need of having this specific electric vehicle. And so we here in Marvel, we have called this the EVO, so electric vehicle in the loop, and will be led by the other. The idea is that this validation plan will be replicable with the aim of being a new standard for future performance tests and safety tests, cutting the development time and cost. Then Eurecat and THI also we will lead the design of solutions related to future battery functionality and safety validation procedures, which we also consider artificial intelligence and miniaturized versions of components. And finally, and most importantly, all these solutions will be evaluated and validated in a detailed and critical way through LCA, LCC methodologies throughout the project. Okay, so this is in a bit what Marvel project is. And yeah, thank you very much for your attention.
Okay, great. Thank you very much, Alberto, for this nice introduction on the frame of the electric vehicle and regulations, geopolitics, and needs for next challenges that the sector needs to address. We will move to start talking about specifically the topic of the lightweight materials. We will start with a presentation on lightweight material solutions for weight optimized electric vehicles and also recycled aluminum alloys and lightweight materials in the battery. Okay, this speech here to present this, we have Manel da Silva, that is researcher at the Metallic and Ceramic Unit in Eurecat. Manel is head of the light alloys research line at Eurecat. He holds a PhD in material science by the University of Navarra, and he has been a researcher in ASCAM, a previous center merged into Eurecat in 2015. Since he has been working researcher from 2008 and currently is managing the light alloys line of the unit of metallic and ceramic materials of Eurecat. Okay, he has more than 15 years of experience working on research projects related to high pressure die casting and processing of aluminum alloys. Then from the other hand, we will have Christian Hannemann, who is researcher in Fraunhofer IVU. And after 10 years in several industrial fields, and since 2007, he's working in Fraunhofer Institute of Machine Tools and Forming Technology. Okay, his hobby and greatest strength is his creativity, involving him in many full international projects related to lightweight design, as well as extensive network activities. Okay. I think the presentation is started by Christian, right? Or
yes, that's
yes,
right.
with concerning this lightweight material solutions, for weight optimized battery housings. So the floor is yours, Christian.
All right, so I overtake. Thanks for the introduction. Yeah, you have heard already something about the Marvel project, and now my job is to tell you something about the lightweight material solutions for weight optimized EV batteries. Yeah, that's an elevator pitch, so I got only 5 minutes left. I tell you something about the lightweight design. I will get a bit closer to CC metal forms, that's closed cellular metal forms, then open cellular metal forms, and in the end, some fiber reinforced plastics, just some impressions of lightweight materials with a potential for the battery manufacturing. First of all, the principles of lightweight design, what are we talking about there? In the first place, we have conditional lightweight design. So you see it on that bridge, the elephant is carried in all the bridges. So if you leave everything away that you don't need, that's conditional lightweight design. So safety issues are secondary in this case. So it's still possible to do the job. So you leave everything away that you don't need. The second one is lightweight material construction. So you use a material that is the lightest possible. And in the case I will present to you, it will be aluminum with a density of 2.7 usually. And the last but not least, structural lightweight design. You see already there can be massive materials, and also you can change the material distribution within the metal. And there are some bits and pieces I will show you in the next slides. So first of all, I tell you something about closed cellular aluminum foam. So we have a material that can easily swim, as you can see right now. It's proven hitting these metal foam cubes in water. So you have a lightweight design with a material that has a density of around 0.7, in this case already 0.25 gram per cubic centimeter. You can imagine all these little bubbles are followed by excellent crash behavior. We have a high stiffness, especially if you use it as a sandwich. And you can use it as a thermal management system if you infiltrate PCM, that's phase change material, into the system. There's no time to talk about that today, but if you're interested, just let me know. And of course, vibration damping is a big topic of these foams as well. The crash behavior, just to show it a first impression, when you see this cup is dropping out of a height of 2 meters onto a steel plate, you see it breaks easily. So if you put a metal foam plate underneath and use the same dropping height, and you see the cup is not damaged anymore. Actually, it dropped on the floor and then broke, but not on the steel plate. Yeah, where can we use the metal foam? You see just some bits and pieces. A thermal conductivity is used for the foam to use thermal management. It's recyclable, it has a good crash absorption, and it's lightweight, as I proved already. So much for the closed cellular foams. Now we come to the open cellular foams. You see already the biggest impression of it. It's lightweight design that you can look through. So that it is penetratable or inflatable is easy to see in this video. The water jet is actually spread and the streaming is changed, but the water is getting through. But the heat doesn't have to go through, so this one proves very easily the heat distribution within the foam structure. You see on the left hand, actually my hand, and on the right hand is a lady from our public department, and she was very afraid to burn me, but as you can see, the flame has about 1000 degrees, and it would theoretically touch me, but the gas flow is distributed within the cellular structure, and the heat is dissipated within the structure. Yeah, so much for the open cellular foams. Last but not least, I got a sample here. I'm not quite sure if you can see me or this material. It's fiber reinforced plastic, and we have a device for the production of profiles in a protrusion process, meaning you have all these spindles with fibers in the beginning. You have a bath where you wetten these fibers with a matrix material, then a tool where it gets baked and brought into shape. And afterwards, it's pultrusion, not extrusion. You pull on the finished product. And this is possible with glass fibers, carbon fibers, and whatever you think of. This is side impact protection for a car, just as one example. And we are able to do curved profiles as well. And that's about it from my side. Just 5 minutes. I hope I'm still in time. And I would hand over to my colleague, Manel.
Okay. Thank you very much, Christian. So I have not that very nice videos you have that I will explain or give some hints about the recycling of aluminum alloys. So on one hand, there is the structural, the lightweight Christian explained, and on the other hand, in order to address lightweight materials, eco-design, and circularity, we need to focus on recycling, on obtaining these materials from a scrap, from recycled sources. On my speech, I will start speaking about some generalities, some fast introduction about recycling of aluminium. Then I will go. I will start speaking generally about recycling of aluminium. Then I will explain some scrap sorting techniques that are currently under development and we are working on in the different European projects. And then I will speak, well, at the end on development of secondary extrusion alloys. That is the process we have selected in Marble for producing the battery housings. And here are results from a different project, but that are directly applied also in Marble production of the battery housings. And I have also added this third point, that is development of secondary high pressure decasting alloys, that we are also working in EuroCAD quite a lot, and it's very important because, well, high pressure decasting is one of the processes with higher future application for automotive industry. As you may know, Tesla it's taking a very strong application on this process by producing the gigacasting, almost one car in a single shot of high pressure decasting. So, well, regarding aluminum alloys, the recycling, it has differences over other metallic materials, because in aluminum it's not possible to reduce any element present in the melt. So whatever you put inside the furnace, you can refine, but it's going to be there at the end. So it's very important to control the chemical composition of the feedstock material, and not just control, but to have it as narrow as possible. The only exception, it's well, very few elements that are more electronegative than aluminum, such as strontium or magnesium, that are lost, and if you increase temperature and time, you can well, even try to reduce it further. So but that's the only exception. Usually, the main impurities, it's well, the main impurity, it's iron, but also other heavy elements such as manganese, zinc, and copper that can be found in aluminum scrap during the refining process will not disappear. At the contrary, they will, if something happens, the concentration will increase. So you have to control very well what you are putting inside, because at the end you will have at least this amount. It's likely that it's going to be even higher, because during the refining process, melt may be contaminated with external tools, iron tools, and also because during the refining processes, you will lose other elements. So the main of the emissions will be of magnesium or aluminum that is easily oxidating that all these heavy elements. So you will have higher concentration. Okay. The only way to reduce it is by diluting it with pure aluminum or with other aluminum that has lower content. So it's very important, the sorting and the selection of the scrap. In order to improve this selection, there are some technologies that are being developed, and some of them are already well, already implemented in industrial sites, still under development, so they are not fully deployed and they are not commercial available, but they are, well, several solutions that are working on this. One of them it's selection techniques and classification techniques based on LIBS, laser-induced breakdown spectroscopy. With this technique, what you have it's a measurement of the chemical composition of each single piece of scrap. So you have a conveyor. Generally, it's done in a belt conveyor. You measure the chemical composition. You, with cameras, you position this particle in the belt conveyor, and then with robotic arm, you place it in the clays, the class of scrap that fits better with this chemical composition. Okay, with that you can have several scrap classes with narrower chemical composition. An alternative technology that we are also working on in a European research project, REVAMP, it's to use neutron activation analysis, so radiation, to analyze a large scrap. Here you cannot separate the scrap, but you can control very well what you are putting inside the furnace. And in the project, we are targeting a device, a prototype, to scan a whole track. So you will have at the end the overall average composition of the scrap present in the whole track. And on the other hand, so on one hand, it's to control what you are putting on, and on the other hand, we are also working on developing alloys that are more robust against variability of impurities. So there are uncontrolled elements, and what we intend is to develop alloys that are not so affected by the presence of a high level of these impurities, or different level of impurities, let's say. For high pressure recasting, we have been working in Salema in a European project on the most typical aluminum silicon, on high pressure recasting alloy for structural applications. It's aluminum silicon 10 manganese magnesium. We have mixed it with a different amount of scrap and analyze the effect the scrap has, the scrap content on alloy properties. And what we have done as for high pressure recasting, one of the main most important properties, especially for formability, it's fluidity. We have developed a fluidity test to analyze the impact that has the scrap on the fluidity. Without any previous melt treatment, what we observe is that by increasing the amount of scrap, we are losing quite a lot of fluidity. Okay, you can see here that by increasing the scrap from zero we have about 75 this value of fluidity. Let's say that it's an average length of this mold here, the different strips of this mold. We are decreasing to 22, 30 with 80%, 100% of scrap. The same for different alloy compositions, that we are decreasing quite a lot the fluidity of the alloy by increasing the rate of scrap. And this is due, to the presence of inclusions, okay, of non-metallic inclusions that due to contamination are present in the scrap. We measure this inclusion content with an alternative technique, pre-filled footprinter, that it's provided by one of the project partners. And with this technique, what you do is you melt the aluminum inside the crucible and you get filtered. There are several inputs you get from this equipment. The filtrated the melting rate, the filtrating rate. So it's decreased. You can see quite a lot when we are using more scrap. The presence of inclusions left in the filter, it's also increased with the amount of scrap. So even if the chemical composition is the same or very similar, what we observe is that the presence of inclusions is higher, so it's required a melt treatment in order to have the same quality of melt. So it's not directly cannot be directly used as scrap as an ingot. And on the other hand, we observe that in mechanical properties, we also conduct mechanical characterization of these different alloy types, and we observe that the impact was very low on the mechanical properties. So the inclusions are present, they affect very much fluidity, but not as much the mechanical properties.
Hi, Manel, sorry to interrupt. Consider we have like 4 minutes left, okay?
Okay,
around.
Yeah. Mm-hmm. And yeah, so I will rush a little. And then also we have worked on the development of these alternative additions of other elements in order to improve the robustness of alloy against the presence, this variability present of impurities. Okay, here also we have done the fluidity analysis. We have observed that with additions of some elements such as zinc, fluidity is highly decreased, and well, which is the impact of these impurities or the different elements in each by each. And even if we can observe again important effect in fluidity, in terms of mechanical properties are not affected. And regarding the extrusion alloys for battery housing, the alloys we are using is in Marble for this battery. We have done quite the same by analyzing the effect of a scrap on the properties of the alloy, and we have observed that in this case the scrap is not that contaminated. So by using high amounts of scrap, the inclusions present in the melt is not highly increased. It remains more or less in the same level, and also the filtration rate and so on. So with the pre-filtered printer, we can see that there are not that much impurities on the scrap. And we also analyze the effect that will have on the formability of the alloy. For high pressure decasting, we analyze fluidity. Here we analyze compression tests at different temperatures and different speed rates. And also the impact, it's minimum. So the impact on flowability, on formability of the alloy, on extrudability of the alloy should be not very large. And in terms of mechanical properties, also we didn't observe any clear trend regarding impact of scrap in the mechanical properties. And well, that's all from my side. I hope I fit the time.
Yeah, yes. You. Thank you very much, Manel and Christian. You just get into the right time. Exactly 12:10. So thank you very much, and also thank you very much for the nice and interesting content of both presentations concerning the materials, lightweight materials for electric vehicles that Christian from Fraunhofer presented, and also all these investigations and research results that we are obtaining through the participation in these three European projects, Revamp, Salem, and Marble, in the concerning the new light alloys, recycled aluminum light alloys. Okay, we'll continue with the webinar then. Thank you, Manel and Christian, and we will now talk about one important part also of Marble concept, no? That is this eco design okay, eco-design concept in the battery. So the integration of the environmental aspect when developing products. In this case, in the case of Marvel, the whole battery, and concerning this webinar, what concerns to the lightweight materials. Okay, this presentation will be done by our colleague Francisco Fernandez, that is a researcher in the Product Innovation and Multiphysics Simulation Unit in Eurecat Technology Center. Fran Fernandez is industrial designer and product developer from Sevilla University, and currently he's working in Eurecat's product development and multiphysics simulation unit as research and development engineer, and he's working on the co-design aspects in industrial and medical sector products. Okay, so welcome, Fran, and the floor is yours.
Thanks, Edward, and hello, everybody. Okay, in that presentation, I'm going to show you what eco-design is and what its rules are. We will continue with how eco-design rules are being applied in the Marvel project. So, the first eco-design is known as ecological design or design for environment, and is defined by the ISO 14006 environmental management system as the integration of environment aspect and product development with the target to reduce the environment impact during the product's life. Eco-design do not want to modify the product's industrial design, process, or services. It's more, it's adding the environment as a part of the briefing and included during the product's development process. And we have, there are two design strategies of the product, linear and circular. The linear way is the traditional route where the product is thrown away at the end of its life cycle. And the neo, no, that means that they generate a lot of waste and not reuse materials. But the circular design, it's a friendly design where the product is reintroduced to the main supply chain like a new material or reusable part. In that context, we are going to talk about cradle-to-cradle paradigm, who is a circular design maybe rule. The paradigm of design cradle-to-cradle is based on a nature and try to imitate it. It's said that the best way to be sustainable is replicate nature, where the waste is not a system, is a transformate into a nutrient for another. As nothing is waste and nothing is wasted. So the important to integrate the environment variable from the start of the work package is important because it's estimated that the 80% of the environmental impact of the life cycle of the product is defined during its design phase. So how we can eco-design our product? In resume, we can use these 10 eco-design rules. The first one is don't use a toxic material. Sorry, don't use a materials and a right closed loop for necessary but toxic one. The other one, second one, is the housekeeping in order to minimize the energy and resource consumption in production and transport. The third rule is waste. In order to use the structural feature and high quality materials to minimize the waste, not interfering with necessary flexibility, impact strength, or functional properties. The fourth rule is energy. In order to minimize the energy and resources consumption to the usage phase, especially for the product with most significant environment aspects. The fifth rule is upgrading in order to promote repair and upgrading, especially for a system development product. The sixth rule is a long life of the product in order to promote the long life, especially for product with more significant environmental aspect of the usage phase. The seventh rule is the protect material. The rule try to use the best material, surface treatment or structural arrangement to protect the product for dirt, corrosion, and wear to minimize the maintenance. The eighth rule is about the information. Provide to upgrading, repair, and recycling through the accessibility, tagging, modules, breakpoints, and manuals. The ninth rule is mix in order to promote the upgrading, repair, and recycling by using few samples, recycled, not blended materials, and no alloys. And the last one, the 10th rule, structure. Use a few joint elements as possible. Use screws, adhesive, welding, snapfish, geometric looking, etc., according to the life cycle scenario. So, in this second part of the presentation, we are going to talk about how these 10 rules are being used in Marvel. Well, the first rule, do not use a toxic material, is done with a mechanical parts and manufacturing using no toxic material. All the material in Marvel are not toxic and are recyclable, except the cells. The second rule is housekeeping, and is done with internal parts are carefully designed in order to integrate and optimize for the volume transportation. The third rule is done with a system weight reduction by 20% and with a new particularly recycled high-performance aluminum alloys for extrusion. In addition, we only use 2 dies to design the modular case to allow us to easily modify its dimension. So we can change the module dimension easily and with the same dies. The fourth rule is minimize the energy, and we reduce the reload time by 25%, and we use an ultra-fast charging strategy and improve the thermal management. Besides, I had reduced the weight by 20%, which means we're saving energy over the life product during his life. The fifth, upgraded, is the solution for sustainable dismantling and second life. And we designed the battery pack to easily change the part as a module or electronic components. The sixth, long life, is done with advanced and flexible management system to increase life. In addition, the store capacity is higher, and our module design allows to extend the life of the battery pack. The seventh rule, protect material, is done with a selection of self-protect materials to avoid the surface treatment. As we said, the parts of Marvel are manufactured in aluminum, which is self-protected. The eighth is information, and in Marvel we done with characterization and validation the producers relative to performance and safety. And not only about the specification. We designed the battery pack specially to let and easily assemble and disassemble with manuals, pokayokes, and visual information. And ninth is the mix and battery pack is manufactured in recycled aluminum, as Manuel and Christian have told on his presentation. And the last one, the rule structure said is done with all parts are easily assembled and disassembled. Full housing is made for a single material, and the welded parts also are made of aluminum. And the housing is not welded, and the dissimilar material parts are screwed together. So, thanks to these 10 rules, as you can see, we have a sustainable project, and the circular cycle is complete. Thanks for your time. Unfortunately, I have a emerging now, and I need to leave. So, if you have any question, feel free to send me a mail.
Okay, thank you very much, Fran, for the presentation. And transmitting this co-design criteria that we are using for development of Marvel battery pack. We will then move to the last presentation, where Magnus Eriksson, from Senior Business Developer in SINTEF Research Center in Norway, will talk about these welding and joining techniques for reinforcing materials that advances in the knowledge of these that were made in the frame of Marvel project. Okay. Magnus, as I mentioned, is a Senior Business Developer at SINTEF Research Center. He holds a PhD in computer-aided design at Luleå University of Technology in Sweden, with focus on ultralight strength steel for automotive applications. Okay, he has been working as a research center director in Sweden and as general manager at the Swedish steel industry SSIB. Since 2011, he's working as researcher director at SINTEF Industry in Norway, with a special focus on welding and structural integrity of steel and aluminum. Okay, so welcome, Magnus, to the webinar. Happy to see you here, and please take the floor to present this topic.
Yes, thank you all, and welcome to one of the last presentations in this topic. And I will talk a little bit about welding and joining, especially in this case, what we talk about welding and joining techniques for reinforcing materials. And specifically for this area of lightweight mobility. So we can say that this is also about welding solutions for optimized use of aluminium, especially when it comes to lightweight optimization and design, where it's certainly important in this case. So first of all, why aluminium? In this case, we choose to make most of the structural parts in this battery housing and the battery systems by aluminium. Aluminium have some good properties, especially for mobility. It has a very low weight versus strength properties compared to many other metals. It is also very good in extrudability and the design freedom, which makes it very efficient to produce and also cost efficient. It has very excellent corrosion properties and heat transfer properties, which makes it good for automotive applications and specifically in this case of lightweight battery housing. It has certainly also low life cycle costs, which is important. And when recycled, aluminium has a rather low energy and CO2 footprint. So it is beneficial in most of the cases, especially when recycled, but it has some disadvantages when it comes to manufacturing. It has a challenge when it comes to welding. So it's in the area close to the weld, it's something that is called heat affected zone, where you have reduced strength. And in design of some alloys, most of the high strength alloy that we use, there is up to 50% reduction of the structural strength you can use. That means that you have to design the whole structure as if it is welded, basically. That means that you might need to design the structure twice as heavy and resource to use than necessary. And this is only because of the small welds. The challenge, basically, I will go into that one regarding aluminium. If you compare an aluminium weld towards a steel weld, in the steel weld you can choose a weld material, and the area surrounding the weld, close to the weld, is often harder and stronger in yield strength than the surrounding material. So the plastic deformation, in case of a crash or in use, it is distributed in the surrounding material, which doesn't create a weak link in the weld. So in globally, there is no strength reduction because of the weld. In aluminium, on the other side, in the alloys that is heat treated by solution hardening and precipitation hardening, which are the ones we are normally using, then the weld metal and the heat affected zone is weaker than the original and the base metal. So in straining or in any deformation, the tension is localized close to the weld, and there it breaks rather easily. And it is also very sensitive to small defects in the weld. So this is the main challenge of aluminium in design. And this then creates a system where you have to redesign or opt to make the geometry much thicker than it otherwise should have been. This is caused by what is called solid solution. During the heating of the weld, if you see in the right picture here up, there the precipitates that has been used to that has been created in heat treatment, they are solid solution in solid solution again, and in the further away from the weld, the precipitates have been coarsening. So they grow and they are coarsening, and both of these zone 1 and 2 are weaker than the original material. We can see it in the picture to the left here, which is measures of the hardness, which represents the strength of the metal. And it is full strength away in the BM, so-called the BM, which is the base material, but then rapidly drops when it comes closer to the weld. And this is an area that is almost 20 millimeters away from the central line on the weld. So it's a rather large area, but still small enough to be very sensitive for straining. And this is also shown here, that is approximately 50% of the hardness, which then represents 50% of the strength. So can we avoid this? Yes, we can do it by a full solution heat treatment, quenching and aging, and that has to be done after welding. The blue line here represents a material weld that we have put everything into an oven again and make the full solution heat treatment and precipitation hardening. And then everything is recreated as long as we use the same material in the welding. However, this is very impractical for complex components and large structures, such as full body car components or aluminium bridges like we have here. So this is a very different and difficult way to go. Can we do something else? Yes, by having an intelligent design where we compensate the soft areas with another geometry and heat dissipation during welding. So by optimizing the area close to the weld, we can, in a way, compensate for this. One example here is by this housing floor that we are using in the marble project. The housing floor consists of hollow profiles where the connections are like the left and the right part of this red picture. When you put them together and weld in the top and the bottom part, we create a weld, and the heat affected zone is then distributed like this. here you can see the blue area representing the weak areas where it's very soft, and the red is the full strength areas further away from the weld zone. By accounting for the geometry with the geometry for the heat affected zone, we can compensate. And does it really work? Yes, here we see a picture of the tension test. I cannot make a movie of it, but this metal in its base metal with the full strength of T6, which is a tempering, it has 310 megapascal, and this tension experiment with all this geometry reach exactly the same strength. So by using the material in the right place and compensating for the weak zone, the rest of the component can be optimized in order to have as low as possible weight. Next level is then to use this by a numerical through process simulation. In this simulation, we are simulating the whole heat thermal field in the geometry, which you see in the picture to the left upper here, with a finite element simulation. This heat history then is taken out from all the material points in the geometry, and we extract those temperature time histories into a precipitation modeling tool that will calculate the strength and hardness based on the history of each of the points. This is then put back in a comparison with measured hardness, like we show here to the left bottom part. And when we see and if the prediction is of high accuracy, we are then assuming that the precipitations are estimated and developed in the same manner, and then we can use this in the lower part in the middle here to use as a strength model, where the strength of the metal is distributed differently based on the heat. And we compare this to the experiments, as you see here to the right, where we can show that their localization and the capacity of the component is as our numerical model. And then our numerical model will be used to optimize the geometry again in a feedback loop. And when the geometry is changed, we will do a new simulation with the new heat treatment, because when you change the geometry, the heat temperatures and the distribution of soft zone will be different from the other one. So this will then be the optimization routine to have as least material as possible with an optimized properties. So that was how we are doing in Marble to optimize the geometry based on the temperatures and the histories from welding. Thank you very much. Questions?
Okay, thank you, Magnus.
Thank you.
So yeah, now let's talk. Let's open for questions. We have already two in the chat. One of them is already answered by Sylvia. Thank you, Sylvia, to Alexander. The other one, Carlos, asks regarding circularity eco-design, do you consider a material sourcing program? How do you get the materials from the end consumer? So are you referring to? I think you can open your mic. But are you referring to the bill of materials, or can you expand the question? The question will be to Tony Lara. Are you here?
Yeah. I see the question in the chat, but I'm not sure if you are speaking about how after the use, the producer use again the material. I don't know if it's related to this, the question, or I don't know if the question is from
Carlos Carrillo.
Carlos Carrillo, are you here?
Yeah, hello. I just wanted to ask, if there is any plan of recovering these parts at the end of the life or not?
In the project?
Yes, yeah.
So after the manufacturing process in ABL of the battery, then TS which is a partner in the consortium, will disassemble the battery and then ABL will again remanufacture the battery with the aim of demonstrating the versatility of the process, so that indeed we can recover all the parts separately.
Okay.
For recycling.
Understood.
So that's why we have a recycler partner in the consortium to guide us in all these requirements from the waste manager point of view. Okay, I don't see any other question in the chat, but you can open your mic or raise your hand maybe, and we will open the mic for you if you have any question. For them, okay.
Yeah. The question for Magnus.
I hear Magnus, so I didn't understand well that played with the heating distribution while welding aluminium.
Okay, yes. Is this the numerical model or the experiment?
At least you can open your mic and.
Yes, can you hear me?
Yes.
Okay. I didn't understood well that plate where you distribute the heating for make the weld stronger in an aluminum material. Could you explain it a little bit, please?
Yeah, if I have understand your question right, then we are using, if you see the lower part here, the lower to the left, let's see if I can have, no, the lower left here, we are simulating the full welding with a numerical model where the heat transfer is in the weld area. And we are simulating the whole temperature distribution in this profile while welding. And this is the upper picture here that are showing the temperature field in the weld, in the area. And then each of the points here in the material is then given a time and temperature history, where the temperature is going to be very high for a very short time and then falling. And this will be very different from each point in the geometry. So this is the middle part here that will show all the points and the cross section of the geometry.
Okay.
So, and this temperature history is then used to assess and evaluate the precipitation in the precipitation growth in the metal, and this is then used in the numerical model of the strength. So, and we are also assessing different means of if the geometry change, like this one, which is hollow, it will dissipate heat differently than if it is smaller or thinner. So we are trying to find the optimal geometry that is both not using too much material, but still using material enough to dissipate the heat.
Okay, understood. Perfect. Thank you.
Was that the answer on your question?
Yeah. It is. And also, I have another question. Is it possible to get all those presentations via mail or something?
Yes.
Okay, how could we do that?
Sorry, I cannot hear you well, but we will write you from the coordination team, also with Marina. We will write you an email with all this information.
Perfect.
Is that correct, yes. Marina? Yeah.
Yes.
So
exactly.
she's already writing. Yes.
The presentations and the recording of today's webinar to all registrants in the mail that you provided for the registration of this webinar in the following days, probably at the beginning of next week. Thank you.
Perfect. Thank you so much.
Well, yeah, I'm sorry if I didn't present it, but I think it was presented. Any other questions regarding this topic?
Yeah, or regarding any other of the topics shared? Yeah, well, maybe I have a question for Manel. I saw that scrap sorting and composition control is an important issue, but is there a strong industrial interest in this kind of solutions?
Well, yes, it's so. Yeah, as you mentioned, the sorting and the control of the chemical composition, it's a must in recycling aluminium. So you need to, so whatever you are putting inside the furnace, you are getting it at the end. So you are not going to dilute it or to reduce the content of any contaminant during the process. So you need to control very well the initial the composition of the scrap of the feedstock material. And there is a lot of people working on this, on improving the control of this composition, and especially of classifying, of separation techniques for better get scrap with a narrow chemical composition. And of course, there is a strong industrial interest on this. Most of the big recycling companies are trying to put some separation equipment or some sorting and improving all the possibilities to, and not just to control the chemical composition, but also to clean, to reduce as much as possible the contamination. They are including the techniques to separate, especially iron, that is the main contaminant, with just by magnetic attraction of the iron. They are using very strong magnets to extract the free iron from the aluminum scrap, and so yeah, that's surely one of the issues that the aluminum recycling industry is targeting the most. They are very concerned about this.
Okay.
Thank you.
Okay. Is there another question from the audience? You can raise your hand. Also, in the meantime, I have a question also for Christian Hofer regarding the how aligned is this integration, the functional integration again? How aligned is it with the circular material concepts, and is there any approach to reduce the amount of needed virgin materials?
Yes, actually, what we use conventionally, we use aluminum powder as starting material and a blowing agent to create the foams. But there are some research activities and already some serial manufacturing of substitutes, which is done by metal chips from milling and turning. So you can break them down in some devices we tested and then use it as substitute. So you decrease the prices for, I would say, about to as low as 12% of the original prices. And so you have a recycling almost 100% because we can work with almost any aluminum scrap that we get. Yeah, we break it down and create foam out of it.
Okay. Thank you, Christian. I see another question that is already been answered by Magnus. Okay. Is there another one from the audience?
I can just add to that one that stamping is.
Yeah, Magnus.
I can just add to that question that stamping is, of course, a really efficient way of designing integrated functions in geometry. We However, the development of tools for stamping in such research projects is a little bit further away than we are planning for. So in this case, we are not stamping, we are using plate materials and extrusion. But in a full production line of a marble battery housing, I definitely think that stamped component could be an option for that reason. But in this research project we are not using it.
Okay. Any other question? Please don't be shy. Okay, see in the chat. Okay.
Just answering Dressel that in the housing we are thinking in, as Magnus say, in extrusion profiles, and only for the plate, for the upper plate, we are thinking sheet metal, and in this piece maybe the stamping, okay, can be an option.
Okay, I think there is a question for Christian here from Francesc now. Are you thinking about battery cooling plates, materials, and forming technologies?
Definitely.
Yeah.
Of course, in the first place, the project is working with extruded profiles from Massage, so the battery boxes built out of them. But on the other hand, when you talk about cooling plates, we have metal foam sandwich structures that can also build the whole battery box. And also we have combinations of open cellular foam together with these extruded profiles. So you can actually combine both and use the advantages of both. So the large surface of the metal foams combined with, for instance, the channels of extruded profiles. So combinations are there, definitely a part of the project.
Yeah, thank you, Christian. I have a question for Magnus as well. Are there other many means of reducing the weakening effect of the soft weld foam? And if it's not possible, to make optimized extruded profiles?
Yes, there is some attempts now. We are doing research regarding improving the strength of the metal, the weld metal itself. So if the weld metal is significantly stronger and stiffer than the surrounding, even though the surrounding is weaker, for instance, in the plate material where you cannot optimize the geometry, then if the weld metal itself is very strong, it can be used to protect localization and drive it away from the area. We have done some numerical simulation in other projects that shows that even though the heat affected zone here is as weak as in the left part, the left picture, I can show that, a strong weld metal in the right part protects the localization and prevents the localization of strain in that area and creates a distribution of the straining. So this is an approach that we are working with and looking into. And we are also studying the possibility to produce these kind of high strength aluminum wires. This is another project and some examples. But the problem with high strength field wires is that they tend to crack when they have a lot of alloying elements. So then we try to solve that challenge by having grain refinement in the wires in order to make them not to crack during solidification. And we have shown that it is possible. These two pictures on the left right here shows that with grain refinements, non-particles in this case, titanium carbides, then you have a really high density of EQXL grains, which creates a non-cracking weld. However, it has some pores but that is another challenge that we can deal with. And some other studies by Fatahi shows that in this case, they can reach significantly higher strength in the weld metal, even though the heat effector zone is weaker. And that, as I said, might protect the weld itself from being the weak spot. This is research we are doing. Thank you very much.
Yeah, there is another question. Let's include this one. So which kind of joints do you use for metallic foams? Okay, Christian.
Yeah, there are many different choices, of course. The easiest one, the conventional use is mostly as a sandwich structure. So the load is carried by the cover sheets. And so if you connect the cover sheets, the foam is just, I would say, a middle of the purpose. It's a distance holder. So if you connect the cover sheets, that is covering the load. So the cover sheets are the most important bit. You can weld them easily by laser welding or whatever system you're using. And also we developed for joints some special inserts you can use. So it's these are metal inserts mass produced that can either go directly into the foam, or they use the cover sheets to lock on the place. And it's possible to use only one cover sheet from one side. So if you have a plate for architecture or something, then you don't want to see the screw on the outside. So you have just an insert that is visible from the back and accessible from the back, and others where you use both cover sheets and you can integrate like high loads onto the cover sheets and into the foam. And I hope that answers the questions. And I saw already there's a second question about working in 3D printing of metal additive manufacturing technologies. There is quite a lot of work in this area. Our institute is working in 3D printing of aluminum, copper, stainless steel, tooling steel, and titanium alloys. So it's almost, I would say, open to many different fields of action. And there are even some possibilities where you can use, you know that there is a difference between casted structures, for instance, and 3D printed structures. So conventionally, what we do, we produce the wax pattern for the master pattern for the casting by wax printing, for instance. And from these master pattern, you can use these to do investment casting and can create such structures in casting. So that is actually as cast, and you see different metals as well. So it's in copper, or it's in aluminum, in stainless steel, whatever you think of. So it can create whatever you can design is possible to cast as well. Actually, at the moment, we go down to details like strut thickness of these cellular structures down to 160 micron. And we always have a competition between 3D printing and casting. So there are some structures where they have an advantage and others where we have an advantage, but both of them are actually used in many processes and the developments.
Okay, so there is no other question. I think we can close here. Okay, there is another one. Okay, so yeah, Christian.
Yeah, close cellular metal foams. I would say energy demanding. Yeah, you have to melt the mixture, so you have to heat it up until the melting point. That's the highest energy demand that you have, and we start usually with chips or powder, and to create this substitute made by chips is a lot less energy demanding. and easy recyclable. When you talk about this, so the foam, it's conventional aluminum, so you can recycle it in the conventional ways. I hear that almost 70% of the material of the aluminum that has been produced in the world is still somewhere around, so the recyclability is quite easy. Just use the conventional ways.
Okay, thank you, Christian. So,
okay, I think we have. Okay. Yes, I think we are approaching the end of the webinar. I don't know if there are other questions, Alberto, that we missed to answer. Anyway, if now you have one question in mind and said, or later after the webinar, or once you receive the materials, or you will be able to download them from the web page, from the project web page, Marvel project.eu. You can also always send us an email, and we will try to consider your question and give you an answer. Okay. So what I encourage you is to follow, check our webpage. We have a newsletter where periodically we inform about the main advances of the project, publication, main results, participation on fair conferences, etc., webinars. Okay, so you can keep posted about the things that we are working in the project. We are more or less in the middle of the project, moving toward the manufacture of our first prototypes by the end of this year. So I encourage you to follow the newsletter, follow us. You can follow us also in LinkedIn, in Twitter. Okay, check these contents, and as commented, if you have any question, you think there is anything you want to comment or discuss with us, feel free to contact us via email, and we will be very happy to provide you with more info or start discussions in any of the topics that we are addressing. Okay, as you know, Marvel, as you have seen, Marvel is a very huge project. We address many topics apart from this material lightweight design. So I hope we will get more. Well, I don't hope it. We will have more webinars in more thematics related to the battery pack performance and design. Okay, so be aware, and let's hopefully see you in next webinars. Okay. Thank you very much for your attention.
Thank you.
And thank you to the speakers also for the nice presentation.
Thank you very much.